So we're going to move into the idea now of when we have functions of several variables. So all throughout Calc 1, you were used to dealing with just y is a function of x. But now we've got a relationship between three different variables. So now z is going to be our main one, and that is going to depend on x and y. So we have two input values, and then we get this output of z. So we want to start by talking about what does this look like, and then also how do we define domains and ranges of these. So a function of two variables which we still use the same notation for. We have a function f, and in this case it has two inputs, x and y. This is just some relation which assigns exactly one value z in some set B to every ordered pair xy in a different set D. Okay. So just like we had a function of a single variable, your input only corresponded to one output. Same thing here, but now my input is an ordered pair. So each ordered pair is only going to correspond to one z value. So to just give you kind of a visual as to what's going on here. Now our domain, which is that input set, is going to be some region in the xy plane. And every single one of those points in that region is corresponding to a third value, which is on the z-axis. Okay. So my domain now is going to look something maybe like this. This is the set D. So all the points in here are some xy values, and every single one of these is going to correspond to an output. So this is how we get these z values. Okay. So this is our domain over here, and then this set of values is going to be our range. So this is that set B we're talking about. So essentially, before you were talking about intervals for your domain and range. Now you're going to have a region for the domain, but you're still going to have an interval for the range because it's what z values that function is going to take on. So the domain of f is the set D. So i.e., this is the set of all ordered pairs where this function f is defined. You still essentially keep the same rules as we did with single variable functions. You can't take natural log of 0. You can't take natural log of a negative number. You can't divide by 0. We can't take the square root of a negative number. So all those rules still come into play, but now in dealing with those, you might have a connection between the x and y values that make that satisfied. And then here, the range of the function f is the set of all values z which is a function of x and y, where these x and y are in the domain of D. So when you're trying to find the range, it's not as important of a concept. So you might have some questions that are on in your homework, but of course you can use a graphing calculator to help you out, like an online 3D one. But it's the same kind of idea as before. Like if you have a natural log function, well, the range of the natural log function is negative infinity to infinity. So even though you might have a funky input, it's likely that that's still going to be the range. And then the same thing if you're working with like parabolas and things like that. You kind of just take those base functions, and even though they've been complicated a bit more, they'll still have the same underlying meaning. Okay, so try to use your knowledge of Calc 1 to just answer those questions. So let's try a few examples. So let's start with our function f of xy equaling the natural log of x times y. Okay. So I'm going to input x and y values, and in return, it's giving me that z value here. Now, the problem with the natural log function is we can never take natural log of 0, or we cannot take natural log of a negative number. So this function is only defined if this product, x times y, is strictly greater than 0. Okay? It's not defined when this product, the thing on the inside, is less than or equal to 0. Okay? So you're trying to figure out the region in the xy plane that makes this true. So if I go ahead and draw a picture, here's our x-axis, here's our y-axis. If I need the product to be positive, well, in quadrant 1, the product of x and y is positive because x and y are both positive. If I'm over here in quadrant 2, one is positive and one is negative, so this doesn't work. In quadrant 3, because they're both negative, the values in here, their product will be positive. And then in this fourth quadrant, again, one is positive, one is negative, so this one doesn't work either. The problem is I can't let my x or y equal 0 because that would give me natural log of 0. So here, the axes are not going to work for me. So what I need to do to actually draw this domain is I don't want to use solid lines. I've got to go ahead and say that I can't actually equal these axes. I can get super, super close to them, but I cannot equal them. Okay? So our domain is going to be these two regions. Okay? So the way we would actually write this is it's the set of values x and y such that x is greater than 0 and y is greater than 0, because that's quadrant 1, or they're both negative, because then their product is positive. So this criteria gives you quadrant 3. And so this would be how we represent the domain. So try a bunch of these out. The next thing we're going to talk about, though, is how can you tell if something is a function or not. So if you remember back in Calc 1, or really even before that, if we were trying to determine if the graph of something was a function, we had a vertical line test. And realistically, the same exact idea applies here. You're just working with a 3D picture. So if you have a surface, thinking back to all of the different graphs that we went through, if you can draw a vertical line and it intersects in only one spot, no matter where you draw it, you're golden. The thing is a function. So that is exactly the next thing we're looking at, the vertical line test. So this states a surface in R3 is the graph of a function of x and y if and only if no line parallel to the z-axis intersects the surface more than once. So exactly what happened in college algebra, pre-calculus, all of those courses. That vertical line was indicating x equaling that number. If it hit in two spots, that told you for that single input, there were two outputs. Same idea here. If I draw a vertical line that's parallel to the z-axis, that's indicating my x and y values are fixed. If it's hitting your graph in multiple spots, then you run into a bit of an issue because that single input xy value has multiple outputs. So to give you an example of this, let's consider the surface x squared plus y squared plus z squared equals 9. Okay, that is exactly a sphere of radius 3, but just to kind of break this down to show you we can kind of turn this into functions. You can solve this for z squared. That's really 9 minus x squared minus y squared. And then taking a square root, when you take a square root, you get a plus or minus. So it's plus or minus the square root of 9 minus x squared minus y squared. Okay. So we consider the surface, which is just a sphere of radius 3. We know that circles do not pass the vertical line test, so a sphere is analogous. It also will not pass the vertical line test. But just to kind of show you, if we go ahead and graph this thing, you can go through all of those different traces. You can also find the domain of this thing. Which really just deals with that trace in the xy plane. Because really, back up here, if you were finding the domain, you would need 9 minus x squared minus y squared to be greater than or equal to 0, which is the same thing as saying 9 is greater than x squared plus y squared. So it's anything inside that circle of radius 3. Okay. So the domain, this is your restrictions. You take all x and y such that x squared plus y squared is less than or equal to 9, which in the xy plane is everything inside the circle of radius 3. So this would be your domain. Okay. But going back to actually graphing this thing, if we were to graph that sphere, do the best we can. You've done this before though. That would be the YZ trace. Then we've got the front of the sphere. We've got the back of the sphere. And then you could go through and do the XY trace too, which again is just that circle of radius 3. So if you were to try to draw a vertical line, you would see it's going to intersect the top and bottom of the sphere in 2 places. So here's the vertical line. When it goes through, it hits the top of the sphere. If I could draw this nicely. In one spot, maybe right up here, and then it hits another spot right at the bottom. Okay. So although this is not a function, because it fails that vertical line test, because of this way that we can rewrite z as a positive square root and a negative square root, you can consider the top and bottom of the sphere separately. And each of those would be functions because they would individually pass the vertical line test. So although the full sphere is not a function, however, the top of the sphere which is f of xy equaling the positive square root of 9 minus x squared minus y squared. And the bottom of the sphere which I'll call g, just to label it something different, it would be the negative square root of 9 minus x squared minus y squared. These are functions. Because we know circles are super important, and in the same way, spheres are very important for us. So we need to make sure that I can break this down into two separate functions. So if you see these pop up, they're really just representing tops or bottoms of spheres. Okay? Now, realistically, we don't have to stop at an input of two variables. You can go into higher dimensions. And we will talk about that a little bit later on, but it's not something that you can actually visualize. Fourth dimension is still something that's important, and fifth and sixth, because it might have different meaning, but you can't get a visual as to what's going on. But when we talk about going through domains of these things and really everything else we're going to do, the same idea extends naturally. Okay? So ultimately, we can have the same type of thought process. For functions of more than two variables. Say we have a function f where we have one variable, a second variable, and you can realistically have as many variables as you want. So I could stop it at k. It could be a function with 30 different input values. Your relationships are going to be very complicated, but you still hold the same underlying meaning. You just may not be able to get a physical graph as to what the domain looks like. Right? But to at least give you a nice example, we can do one that has 3 input values. Let's find and sketch the domain of the function. And in this case, we're going to have a function with 3 input values, so we can just use x, y, and z. And this is going to be the square root of 1 minus x squared minus y squared minus z squared. Okay. So if I'm dealing with the square root, I always need the expression underneath to be non-negative. So for here, we need this full expression, 1 minus x squared minus y squared minus z squared, to be greater than or equal to 0. So natural logs, you always need the expression inside to be greater than 0. Square roots or even roots in general, you need the full expression to be greater than or equal to 0. But this is really the same as saying 1 is greater than or equal to x squared plus y squared plus z squared. Okay? So if you made this an equal sign, that's exactly a sphere of radius 1. So if I'm saying take all x squared plus y squared plus z squared, so it's at most 1, it's everything inside the sphere. Okay? But what we can say immediately from here is the domain is going to be the set of all x, y, and z values such that this condition holds. Okay? But again, all this is the points inside a sphere of radius 1. So they're all points inside and on the sphere of radius 1. Okay? Because we have that less than or equal to. So this is something I can actually graph the domain for. It is a nice enough three-dimensional function. So our sphere of radius 1, if you were to do that xy trace, it would look like this. And we've got the yz trace, which that is not a great circle, but that's okay. And then the xc trace. So it's everything in and on, so we would go ahead and shade everything inside of here. And that is the domain of this function. Okay. Let's try one more of these before we talk about the last concept of this section. And we'll jump back to a variable or a function of two variables. Same directions though, we're going to find and sketch the domain of the function. And our function is two variables as the input, x, y. We've got the square root of 1 minus x squared minus the square root of 1 minus y squared. Okay. So I'm going to consider both of these separately because I want to make sure both of these have values that make sense. So we actually need two things for this. We need the first square root, the thing underneath it, to be greater than or equal to 0. And we need this other expression to be greater than or equal to 0. So working with this first one, this is saying that x squared has to be less than 1. And yes, technically you can take a square root it here, but remember you would get an absolute value of x from that. Realistically, if x is trapped or x squared is less than or equal to 1, it means x is trapped between -1 and +1. If this was a 4, that would be -2 to +2. But again, all that really comes from is if you take a square root, then what you get is 1 is greater than or equal to the absolute value of x. And that breaks down to this inequality. Okay? And then this ends up being the same thing over here. 1 has to be greater than or equal to y squared. So really we can take any y value between +1 and -1. So ultimately the domain is going to be all xy values such that x is trapped between -1 and +1, and the same thing is true for y. Okay. So if you think about what this domain actually looks like, the most I can go out is 1 in every direction. My x value is trapped between +1 and -1. So the most it can go right is here. The most it can go left is here. But then the same thing is true for my y values. Okay. So my domain is really just going to be a square. So anything inside this square or on it will make sure that both of these square roots make sense and we don't have imaginary numbers. So we've got one topic left in this section that we're going to work on, and that's going to be a concept called level curves. So if you've ever looked at like a topological map of like a mountain or something, you're used to kind of seeing all those little squiggles and then it might be like closer, they might be closer together. That's kind of indicating what the mountain range looks like in 2 dimensions. This is exactly really a level curve. It's kind of if you've taken that mountain and you've sliced it with planes, what that intersection looks like. So it gives you just an idea of like steepness and what's going on in that 2 dimensional surface or in that 2 dimensional plane. So we're going to deal with the exact same concept here. It's kind of like finding traces for fixed values of z. So if we were to take that image or that 3D surface and we were to slice it with planes, this is what it would look like. So this isn't really anything new. It's just an extension of what we've already learned when graphing. So ultimately, the level curves of a function which has 2 input values, x and y, are just the curves with the equations where the output is equal to some constant k. So basically we're saying, if I fix this z value, what does the surface look like on that plane? And that's basically just finding the trace. So this looks at the intersection of a function with the plane z equals this constant k. So i.e. this is just the trace on z equals k. Okay? Nothing more. So let's do an example of a surface that we've already graphed. And then we're going to go ahead and we're going to use find a bunch of level curves. We're going to find the domain and range of this thing so you can kind of see that process. And then we're going to go ahead and we're going to graph the function from there. So let's let f of x, y, be the function 5 minus the square root of x squared plus y squared. Okay. So we've already graphed this thing. Remember, it's a cone. These are just like normal transformations. The negative sign would go ahead and flip it, and then the 5 ends up being that vertical moving up, but it's just doing it in the z direction. So we're going to let this be our function. We're going to find the domain. The range. We're going to graph a few level curves. And then we're going to use all this to graph the function. Okay. So let's start with our domain. When we're dealing with a square root, that's the only thing that can pose a problem. So ultimately, we need the thing underneath the square root to be greater than or equal to 0. But if you think about it, x squared, always non-negative, y squared, always non-negative. There are going to be no problematic x values here. So this is always going to be true for us. So ultimately, the domain is everything in R2. I can pick any xy value that I want. Okay. Moving on to the range, this is one we actually can find the z values for. So we're basically trying to see what values will this thing take on. Okay. So thinking about this square root, we always know the square root's output is non-negative. So let's actually move this over here. So since the square root, x squared plus y squared, is definitely going to be greater than or equal to 0, when I make that negative, it just flips the inequality. Okay. And then ultimately, I've got to add 5 to both sides to get my expression here. So I'm going to go ahead and add 5. And this gives me 5 minus x squared plus y squared under a square root is going to be less than or equal to 5. Well, this is exactly my function. So the output of my function is going to be at most 5. Okay, so that's exactly what our range is. I can go from negative infinity up to 5. Okay, so that is the biggest z value this function will ever take on. Okay, so now that we have this idea of the domain and range, let's figure out what these level curves are going to look like. Now, realistically, you can go about this a couple different ways, but basically all you're doing is you're going to set this equal to some constant. And then you're going to pick a couple values for k to figure out specifically what those equations are going to look like. What I like to do in general, though, is just find an equation for my level curves, and then I'll substitute my values in for k. So here your level curves will be set the expression equal to some constant. Well, that just means 5 minus the square root of x squared plus y squared is equal to some constant. Okay. I'm going to get x and y by itself, so we're going to go ahead and move the 5 to the other side. So this is going to be k minus 5. And then to get rid of the square, let's go, or to get rid of the square root, let's square both sides. The negative also disappears and gives us x squared plus y squared is equal to some constant minus 5 squared. Okay. So I'm just going to be replacing this value of k by 0, 1, 2, 3, 4, 5, whatever it is. In this case, the most I can go is 5 because of the range. So ultimately, this is going to represent a circle. So all of my level curves, meaning any way I slice this 3D shape, it's going to intersect in a circle. Okay. So what I'm going to do is I'm now going to pick specific values of k to see what the equation looks like for that. So I'm going to pick k equals 0. I'm going to pick k equals 1, 2, 3, 4, and then 5. Okay. And 5 is the biggest z value I can go. You can pick negative ones if you want to, but picking like 5 or so is typically enough. On any exam, I would give you the specific values to pick too. So starting with the first one, if I plug in k equals 0, that gives me x squared plus y squared is equal to 0 minus 5 squared. Well, 0 minus 5 squared is negative 5. When you square it, it just makes it positive 5. So this gives me a circle of radius 5. Okay. So simultaneously, while I find these specific level curves, I'm going to go ahead and graph these in that two-dimensional surface. Now my graphing might not be 100% perfect, but that's okay. So each one of these is going to be a distance of 1. And I don't really need to label all of these. Okay. But my first level curve, when k equals 0, I get a circle of radius 5. So go ahead and graph that to the best. Not too terrible. Okay. So this is, oh, that's k equals 0, not k equals 5. This is what the intersection of the xy plane looks like with my surface. So my z value is equal to 0 here. If I pick my z value to be 1, this gives me x squared plus y squared is 1 minus 5 squared, which is negative 4, so this becomes positive 4. So if I move up a little bit, now I'm getting a smaller circle. So when z equals 1, I'm having an intersection of that plane with a circle of radius 4. So that level curve looks like this. Moving inward now, when k equals 2, oh, wrong tool. That gives us x squared plus y squared equals 2 minus 5 squared, which turns into positive 3. So you can see as my z value gets bigger and bigger, I'm getting smaller and smaller circles. So that one gives me a circle of radius 3. And again, doing my best because my spacing wasn't 100% great. Okay. So these should be nice and concentric circles. Let's try to make them a little bit better. Oops. Let's try to move this one over a little. There we go. It's a little bit better. Okay. Moving on to my next value of k. This would be x squared plus y squared is equal to 3 minus 5 squared, which is 2 squared. So now we've got a circle of radius 2, which will look roughly like this. Moving on to k equals 4. That's x squared plus y squared equals 4 minus 5 squared, which is 1. So we get a circle of radius 1. And last but not least, when we let k equal 5, that gives us x squared plus y squared is 5 minus 5, which is 0. So really we're getting a single point here, a circle of radius 0. So that just goes through the origin. Okay. So again, this is basically giving me that bird's eye view. If I look directly down the z-axis, this is what I'm seeing. I'm getting basically a cone coming up to this sharp point, the most being my z value of 5. Okay. So the nice thing about these level curves is it helps us get a really good graph in 3-dimension, because again, it's giving us more input or more traces essentially than if I were just doing the xy plane, the yz plane, and then the xz plane too. So it's giving me a better picture as to what's going on. So basically, as my z is increasing up to 5, I'm getting smaller and smaller concentric circles. If I picked negative values for k, that would give me a visual as to what's going on in the bottom 4 octants. And you would see your circle's just going to keep getting bigger and bigger and bigger the further you go down. Okay? So we can utilize this now to get a very good picture as to what's going on in 3-dimension. And I do want to move this down with me just so I can show you. Okay. So drawing our three axes. We've got the x, the y, and the z. And then I'll go ahead and also draw the negative side, but I want these to be nice. So let's go ahead and use the actual tool to make it dotted. Not worrying about the negative because I didn't pick any negative values for z. Okay. So starting with this first level curve, when k equals 0, that's exactly what's going on in the xy plane. So it's giving me a circle of radius 5. So we're having a pretty large circle down here in the xy plane. Okay. Now when I move up to k equaling 1, that means my z value is 1. So basically, if I were to slice this three-dimensional figure at z equals 1, then I'm getting a smaller circle of radius 4. So when I move up just a tiny bit, I'm getting this circle here. Okay? So this is when k equals 1. Now moving inward again when k equals 2, so I'm moving higher up my graph. I'm getting an even smaller circle again. So you can see these circles are just getting smaller and smaller and smaller. And this is the level curve when k equals 2. Moving on to 3, even smaller circle, even higher up. So that gives me a circle like this. And then when k equals 4, even tinier circle. And then finally, when k equals 5, you hit that point. Okay? So ultimately, we're really just getting a cone that's been flipped and turned around. And I can draw the front of the cone if you really want to, and then the back of the cone would be dotted. So you can take any of those surfaces that we've already discussed in depth, and you can go ahead and slice them now to see what those intersections look like, and you're creating that topological map. Okay, so ultimately, this is what the graph of this function looks like in 3 dimensions. Okay, let's do one more of these, and we're actually going to go back to that saddle-looking graph. So we're going to sketch the level curves and then just sketch it in the XY plane. But this way it can help you a little bit with that 3D visual of the really funky looking saddle. So our very last example is going to be sketch the level curves for the function. Which is x squared minus y squared. Okay. So unfortunately, depending on the value of k, you're going to get different types of level curves. So the level curves are the following. We have x squared minus y squared equals a constant. Okay. So you can think for some values, this is going to be hyperbolas. X squared minus y squared equals 1. Even if I input negative values of k, it's just going to switch the order of these two. So it would still be hyperbolas. The only value that would make this not a hyperbola is if k is equal to 0. So basically, in the xy plane, you're going to have a different level curve. Okay? So for k not equal to 0, these are hyperbolas. So again, I'm going to pick just some values. I'm going to do some positive, some negative in this case, because that changes what the shape is based on positive or negative values. Back with this example, no matter my value of k, I had a circle. So I would know that this just keeps continuing down forever in this direction. Okay. So here the value of k does matter. So I'm going to pick some positive and some negative. And then I also want to pick 0 because I know that will change things. So we'll do -2, -1, 0, 1, and 2. Starting with -2, that gives us x squared minus y squared equals -2. And just flipping that, it's really y squared minus x squared equals +2. Okay. So since the y squared is positive, that's telling you it's going to open in the y direction. When k equals -1, really same thing. X squared minus y squared is -1. Just rearranging these by multiplying by -1 gives you this. So these two open along the y-axis. Okay. When k equals 0, that gives us x squared minus y squared is 0, which is the same thing as saying y squared equals x squared. And then remember, when you take a square root, you get a plus or minus. And then also, with one of the variables, you need an absolute value. So really what you get here is y equals plus or minus the absolute value of x. Moving on to k equals 1, that gives me x squared minus y squared equals 1. And that's nice. I don't have to do anything. This is a hyperbola that opens on the x-axis. And when you plug in 2, that's x squared minus y squared equals 2. So both of these open along the x-axis. Okay. So I'm going to graph each of these, associate a different color for each one. For -2, we'll do a green. For -1, we'll do a blue. For 0, we'll do K. For 1, we'll do orange. And for 2, we'll do yellow. Okay. So I'm going to go ahead. See, I don't like this line. That comes with my note app, so we're going to go and move this down to make it nicer. Go. Here is our y-axis, here is our x-axis. And I'm going to go out 2 in every direction. Okay. So starting with k equals 0, that gives us the plus or minus absolute value of x. So positive absolute value of x would cut these in half, and negative just does the opposite. So we get that giant X. So this is the level curve for k equals 0. So again, in that xy plane, you have these two absolute value functions. Let's do k equals -1 next, because that's a little bit easier. This opens in the y-axis. And remember, this will basically tell you how far you're moving in the y direction, because this is like everything divided by 1 equals 1. So in the y direction, I move a distance of 1. So I would go through 1 and -1, and then we open in the y direction. So we have a hyperbola looking like this. So this is my level curve for k equals -1. Okay. When you move on to this one right here, when k equals -2, you'd have to divide everything by 2 to get a 1 over here. And that would tell you in the y direction you move a distance of root 2, which is roughly about 1.4. So really you're going to go through around here on both of these. So when k equals -2, we get another hyperbola in this direction. Moving on to k equals 1, same thing here. I'm going to now open along the x-axis because I have a 1 on the right side. This tells me I move a distance of 1 in the x direction. And then likewise here, to get a 1 on the other side, you've got to divide everything by 2. So in the x direction, I've got to move a distance of root 2, which is about 1.4. So you get the same kind of shape this way. So if you were to take that saddle, this is what that visual would look like if you were staring down the z-axis. Basically, in these directions are what's happening in the top. You're getting those hyperbolas that go up and up and up. And then in these directions, you're getting that graph going down and still having that curving shape. So it's giving you that saddle figure.